University STEM courses want you to use application and analysis to solve problems. In the past, you may have relied more heavily on remembering and understanding basic facts to get through course content, but at university you will need to ask more application-based questions like how, what, and why to further develop your higher-order thinking skills such as application, analysis, evaluation, and creation. Students often report that when they come to university out of high school, that the course content seems to move much faster and that it can feel difficult to keep up at times. Students also report being surprised by the complexity of questions on tests and exams. They identify that it can be difficult to know how to prepare for these types of questions. It's not only the types of questions that can sometimes feel intimidating on tests for students, but also how much they are worth. Often at university, tests and exams are weighted more heavily, meaning they are worth more of your overall mark in the course than they would have been in high school. The reality is that university learning requires more complex thinking and problem-solving skills than high school. Each incoming student to Western has already demonstrated they have the capacity to succeed in developing these higher-order thinking skills simply through your hard work in your previous education and your acceptance to Western. To understand what university-level STEM learning requires and how you can enhance your thinking and problem-solving skills, let's look at Bloom's taxonomy of learning. The revised version of Bloom's taxonomy of learning shown here was completed in 2001 by a group of cognitive psychologists, curriculum theorists, and researchers. In Bloom's taxonomy, knowledge forms the basis of the 6 cognitive processes outlined in the pyramid: remembering, understanding, applying, analyzing, evaluating, and creating. Being able to remember and understand course content are important cognitive processes and are a required basis for the higher order processes like applying, analyzing, and evaluating information. Let's look at an example related to graphical analysis to highlight the difference between the remembering level, application level, and creating level of Bloom's taxonomy. Let's first imagine that on a test, your professor asks you to identify the parts of a graph and identify the type of graph. This is an example of the remembering level of Bloom's taxonomy. It's an important basis for building your knowledge of graphs, but does not allow you to apply your learning in a more complex way. For example, you may recognize this graph shown here as a histogram, identify the x and y axes, but you have not yet applied your understanding in any way. Now let's suppose your professor asks you to interpret the trend based on this graph. This is asking you to apply your working knowledge of graphs and interpret a set of data. This is the application level of Bloom's taxonomy. Building on the prior example, you may come to the conclusion that this histogram represents a population of birds with varying beak length. You may come to the understanding that the average beak length in this population is somewhere between 38 to 51 millimeters. To come to this conclusion, you had to ask yourself, what does the shape of the graph mean? Or how might the shape of the graph be interpreted? In doing so, you've moved beyond your basic knowledge and understanding of graphs and applied this information to solve a more complex problem. Finally, let's suppose your professor asks you to create a graphical representation of a set of data, or interpret and analyze this information. This is a much more complex question. Here, you must not only have a foundational understanding of different graphs and what they represent, but also how to take a concept and represent it graphically in an appropriate manner. This is the creating level in Bloom's taxonomy. For instance, your professor may give you a set of beak length data about birds in the same population as before, but at different periods in time. They may then ask you to determine what selection pattern is present in these birds. As before, you have to remember the basics about graphs, but you now have to create new information from what has been given and what you already know to answer this question. Questions like, what am I trying to show? How can I show this most effectively? Why would graphing the data help answer this question? Allows us to come to the understanding that a histogram can show the variation for a given trait in a population. In this case, the shape of the histogram can tell us what version of that trait is most prevalent. Comparing the shapes of these histograms allows us to infer that a directional selection is occurring, where the population of birds is evolving to have longer beaks. So as you can see, we can help ourselves reach these higher order levels of thinking by asking why, how, and what when learning new material. This helps us be reflective with our learning. If you know something, you should be able to explain it out loud to yourself or someone else. If you don't know something, you can start by identifying what you don't know and determining how you can find the answer.